Good afternoon, everyone, and welcome to this impromptu EOL seminar. I'm pleased to welcome our speaker, Dr. Bart Geerts, who is visiting from the Atmospheric Science Department at the University of Wyoming. Dr. Geerts received his PhD in atmospheric science at the University of Washington under Peter Hobbs. Currently, Bart conducts research into cloud-scale to mesoscale atmospheric processes with an emphasis on airborne radar data. Much of his research builds on field campaign observations, and he has led several recent multi-institution field campaigns. He has advised 20 master's students and 10 PhD students during his tenure. Dr. Geerts is the PI of a $15.8 million NSF Mid-Scale Research Infrastructure Award that is building the next generation King Air atmospheric research aircraft. He is a fellow of the American Meteorological Society. Dr. Geerts is giving a talk on vertical motions forced by small-scale terrain and cloud microphysical response in extratropical precipitation systems. For those watching virtually, we are using Slido to pose questions that you cannot type in at any time during the seminar, and the Slido interface is located below the presentation screen if you scroll down. Dr. Geerts, welcome to EOL, and the podium is yours.
Thank you. Good afternoon, everyone. It's an honor for me to be here and to give a seminar. So I need to acknowledge first and foremost people I've been working with, especially our new radar scientist, Colton Grasmick, who was a PhD student with me, and Bob Rauberg, Troy Zaremba at University of Illinois, Lulin Zouwe here at NCAR, Katja Friedrich at CU, and then the entire SNOWY team. And I'll talk about SNOWY in a moment. It's a campaign looking at these wintertime frontal precipitation systems over mountains in Idaho. Basically, this research is motivated, the specific question that I'm going to ask is motivated by a question of where does precipitation fall, and that's especially important in the western US, which is relatively arid, and as you can see, there's a lot of spatial variation in annual precipitation, and we don't really sample that very well. It's very difficult to measure orographic precipitation. The top distribution there, this is a large-scale map, and it's a stage 4 NCEP precipitation product, which is radar-based, but then gauge-adjusted. It's if you look especially in the northwest there, it looks fairly different from PRISM, which is entirely gauge-based, and then it's interpolated to a terrain-dependent grid down to a 1 kilometer resolution. And the question is, how accurate is that precipitation at the finer scales? For instance, the scale that is shown here, you can see 20 kilometers down in the lower left there. So we're zooming in much more. This is in Chile, just a mountain range, and Nalbuta range, showing precipitation from a number of gauges there on the right side, and on the left side, WRF simulations, and they correspond reasonably well. This environment is dominated by rainfall, but there's a remarkable dependence on terrain and precipitation amounts, orographic precipitation. When it's dominated, especially by these frontal systems, it's remarkably dependent on elevation. So the question is why? Well, one can argue, of course, that differential evaporation is important. The cloud base is relatively high, but in wintertime, cold environments, that's not going to make much of a difference. So maybe enhanced precipitation growth over ridges, and there's been a number of papers speculating on the importance possibly of a release of instability, potential instability due to orographic lift or gravity wave uplift that then can trigger precipitation. So basically, what I would like to do is to look at the vertical motion patterns over terrain, mesoscale terrain. And when I say mesoscale terrain, these ridges that we'll be looking at are like 10 to 25 kilometers apart, a series of ridges. And relate that vertical motion to clouds and precipitation, ultimately related to that question of the fine-scale spatial distribution of precipitation. So the snowy campaign was conducted in the winter, early 2017, in the mountain range in the western US, specifically the Payette Basin, sloping from the Snake River Plains to the Central Mountains in the east. Used a Dow radar up on a mountaintop, and King Air, University of Wyoming King Air, with its profiling radar. And when you look at that terrain, you can see, as I said, there's multiple ridges oriented north-south, and I label these ridges from 1 to 7. And we flew fixed tracks. It's rather unusual and maybe boring to fly back and forth along fixed tracks, and we had a good reason to do that. These tracks were essentially oriented along the wind, so in case of westerly flow, we would fly track A. Back and forth, like 10 times to 12 times until we ran out of fuel, essentially. Just as a matter of reference, the precipitation climatology is shown here on the right side. This is from PRISM at the 1 kilometer resolution over that same time period, roughly, climatological. So this is sort of the precipitation pattern that you expect. And it's a lot of fine detail in there, and you can relate it to terrain. Some of these ridges that you see on the left, they have, they're purple here in the precipitation amounts. But all this is based on just 8 gauges, 8 snow-tell sites. Those are the black dots that you see here. That's it. So everything else is interpolated relative to the terrain. So there's a lot of, I guess, imagination or algorithm rather than ground evidence. So looking at precipitation distribution from that Dow radar that I mentioned before, for the 4 IOPs that we're looking at in this study, they don't really show that same pattern that you see in this image. The radar is at point number 4 there, at that ridge, and radars don't see very close to the terrain, even though this is a low elevation angle. Still, at the outer range, you go up some 500 to 600 meters from the radar elevation. And the lowest few hundred meters or kilometers is really important, apparently, in precipitation growth. You can see, well, there's maybe some maxima on some days over the terrain, but then you can see this drop-off behind this ridge number 5. Radar coverage is pretty poor here, even though that's only like 30, 40 kilometers away. The maximum range is 45 kilometers. So the radar itself doesn't really give, a ground-based radar, doesn't give you a good feeling for, or doesn't capture that spatial distribution of precipitation all that well, suggesting that precipitation growth is really a shallow phenomenon in these wintertime systems. So we decided to look down, essentially, using the vertical vantage point of the Wyoming cloud radar. It's a 3 millimeter 95 gigahertz radar. It's been used extensively. It's very highly spatially resolved in the vertical and in the horizontal. And it gives you not just the vertical velocity, but also the long track velocity through the combination of the slant forward and the nadir beams, so that you have, you can decompose this or synthesize these 2 radial velocities into a long track and a vertical velocity. And when you look at these radar transects, there's a lot of fine scale structure in the reflectivity, and especially in the vertical velocity. Here you can see some vertical velocity patterns. Top panel for these 4 different examples is reflectivity. Bottom panels is the vertical velocity with rising motion in red. The flight track is the dashed line, the flight level. Radar looks up and down, and the underlying terrain is shown in gray. And we often see these very interesting patterns. These are sometimes Kelvin-Helmholtz patterns in most cases here. Kelvin-Helmholtz patterns, there's bound layer turbulence. Sometimes there's cloud top generating cells. But then there's also terrain-driven drafts. For instance, in this image, there's some red rising motion on the upwind side. In all these transects, the flow is from the left to the right. So rising motion on the upwind left side and sinking motion in blue in some places on the right side of the terrain ridges. So we're interested in separating the transient features that we see in these immediate, these high time resolution images, these snapshots, if you like, from the stationary patterns, the more long-lived patterns that you typically see in model output, especially, high resolution model output that captures the terrain, not LES, doesn't really capture these fine scale transient eddies, but it captures the terrain-driven flow better. So in order to compare against models, we really need to composite. That's essentially why we fly along these fixed tracks back and forth repeatedly, either track A or track B. And that compositing allows us then to essentially suppress the transient signal and retain the terrain-driven stationary pattern. So we're going to talk about vertical velocity. Just want to highlight that estimating vertical velocity is not that trivial from an aircraft. You know this better. Some of you have been working on this. We use a 5-hole gust probe on a boom in front of the aircraft. These are average velocities for the 4 different flights that we're going to look at. And you can see there the mesoscale, this is 100 kilometer long legs. The mesoscale vertical velocity is not 0. It's close to -1 on 2 flight legs. And you wonder, is that real? It's not clear to me. There's some uncertainty there in the measurement of vertical velocity. It relates not so much to the uncertainty in aircraft motion or in attitude variations. Those things are measured pretty well with GPS-aided INS system. What's more uncertain is the attack angle of the flow relative to the pressure perturbations that are measured at the gust probe. We estimate this. We measure this for these cases, but there's uncertainty there. And there's some drift there too. You can see all these trends, they tend to go down. That relates to the fact that the pitch angle decreases somewhat during the duration of the flight as the weight of the aircraft changes. So basically we assume what other people have assumed, that we ignore the mean velocity that is plotted there. We look at the perturbations, that W prime, that is standard in boundary layer studies. We do this for the mesoscale study as well. So to the extent that W bar, the average velocity over the entire 100 kilometer track, is 0, we have an accuracy on the order of 0.1 meter per second at flight level. Now for the WCR, the cloud radar, the vertical velocity profiling, we've been doing that for a long time, using the known beam pointing angle. But we, in this study, went a little further. The first step we do is to remove any, so that the antenna doesn't quite look exactly down. It approximately, and it varies in time. The known beam angle, time-varying beam angle, is being used to basically to remove contamination to the horizontal wind in the quasi-vertical beam. And that gives us a first estimate of hydrometeor vertical motion. Okay, but we want to get vertical air velocity. So we make 2 additional assumptions. One is the same assumption that we do make it for the gust probe. That is that the average vertical velocity at any given level, the WCR is profiling. We do this for 1 level at a time. At any given level, the mean vertical velocity, vertical velocity, is 0. And the second assumption is that the fall speed is uniform horizontally, such that the average fall speed is the same as at any one location. Or, when you assume that the mean air vertical velocity is 0, then the average fall speed is basically the hydrometeor velocity at any level over the entire length of the leg. So that locally, your vertical velocity, air vertical velocity, is the measured vertical velocity, the hydrometeor vertical velocity, minus a height-dependent fall speed. And this was first developed in collaboration with Troy Zaremba at the University of Illinois, and that just got published. So we use the same assumptions, and basically we're going to composite. In this case, for this flight, I think we had 9 legs, and I'm just showing 3 of them vertical velocity. So in this case, there was precipitation. You can see snow converting to rain, accelerating down. Red is a stronger downdraft. You can see some terrain-driven up and down draft here. Flow again is from the left to the right. You can see that snow makes it further down in these valleys probably. Then towards the west, there's some slope in the freezing level. Anyway, we average all this, and we come up with the hydrometeor vertical velocity. This is the average hydrometeor vertical motion for 9 flight tracks over a distance of 90 kilometers or so. And we then subtract the fall speed, and we obtain the air vertical velocity. And now you can see a very good relationship between the terrain and the vertical motion field. For instance, this ridge here seems to have a dipole of rising motion on the west side and sinking motion on the east side. And then in this valley here, there is this ascent. This valley too, there is an ascent, and that's probably a resonant response to the subsidence. So if air sinks from this peak, it reaches a point where it wants to come back up, essentially as a, maybe not quite a hydraulic jump, but a resonant response to the subsidence. So we ran, Lula and Sue ran a simulation for these 4 flights at 900 meter resolution, 81 levels using the Thomson Eidhammer microphysics scheme. And remarkably, for this particular flight, the vertical structure of vertical velocities is very similar. For instance, you see the same updraft on the upwind side of a ridge and downdraft behind. You see the resonant lee ascent here as well as here. This one sort of merges with an ascent that's associated with that peak. But you see that in the observations as well, there and there. So you see this, like in this valley, there is a resonant updraft. So these are averages of vertical velocity over 9 different legs. And at that point, you can really compare observations and modeling well. Observations are often, especially high spatial resolutions, in a way, they're difficult to compare to models because you don't have enough, your sample size is too small. You don't have the full distribution of possible flow patterns, if you like. So compositing helps to come to a point where you can directly compare against model output. And really the comparison is remarkably good, which is promising, and that leads us then to ask questions about clouds and precipitation, which respond, of course, to these vertical motions. One minor difference may be that the amplitude of these up and down drafts in the model is a little bit higher than in the observations. You can see that when you look at the distribution, the black line is the median. The 90th percentile, 10 and 90th percentile are shown in blue and red, with dashed lines being the model. And you can see that the model amplitude is larger than the observed amplitude of these waves. So in a way, the model overestimates these vertically propagating gravity waves. And as I mentioned, we can estimate the along track motion to the combination of the slant forward and the nadir beams, the vertical plane dual Doppler, and that yields the color field that you see here, the WCR along track wind below flight level only. And these lines that you see here, and that were in the previous image too, they're basically the hydrometeor trajectories. They show how snow particles fall and then melt and then become rain down below. So these are true hydrometeor trajectories. There's really no assumptions made. There's no assumption about vertical motion. It's measured directly. Horizontal motion is measured directly. The only assumption there may be that, you know, this is not quite a trajectory, but rather a streamline. But since this is an average over 3.5 hours, it really can be thought of as being partial trajectories. Anyway, you can see a fairly well-developed boundary layer there with a slower flow that slopes over this terrain. And then the model produces a very similar vertical velocity pattern. There we go. The acceleration with height looks fairly similar. And you can see an east to west difference there. And so when we look at the perturbation velocity, subtract the height-dependent mean at each level, you can see convergent flow. You can see that it's stronger here, say at 3 kilometers, and at 3 kilometers towards the east. So the U prime, the perturbation velocity, is towards the west here and towards the east on the west side. So there's this convergent flow at low levels. And the model does this too. The details differ, but essentially there's significant along track cross-mountain convergent flow. And you know, from first order principles, you expect then the air to rise on this scale. So the question about mesoscale vertical velocity is coming back. This suggests that there is, you know, low-level convergence, ascent, and then mid-level divergence. Unless there is compensating flow in the cross-track direction, in the along ridge direction, in and out of the page, that we don't know. But if you vertically integrate the vertical velocity from observations, that's a black line here, WCR, you get this ascent up to 0.15 meter per second, 15 centimeters per second. That's just the magnitude of the low-level convergence and, you know, simple vertical integration, not even accounting for density variations, just the first order back of the envelope calculation. You do this for the model as well, and you get a similar pattern. And the dashed or the dotted line here shows the actual model mean vertical velocity. So this is simply from continuity equation. The solid line, the dashed line is the actual vertical velocity in the model. So yes, there is mesoscale ascent, and yes, it's primarily driven by this you know, low-level convergence over sloping terrain, although there's some compensation because these estimates are larger than the actual one. So you can then ask, well, why didn't we include the mean vertical velocity in our WCR vertical velocity estimate? And we could use this profile to add to the WCR vertical velocity as an independent estimate of this mean vertical velocity. Models do much better for this W bar than observations, but then models still, you know, have some uncertainty, so we didn't want to mix model with observations and decided to stick with the idea that W bar is 0 for simplicity. Anyway, it's not very large, 0.05, whereas the amplitude of the waves is more like 1 meter per second. So synoptically, this environment, I want to talk a little bit more about clouds and precipitation, and leading up to that, I need to say a little bit about the flow pattern, essentially an atmospheric river coming over the Pacific Ocean in a warm sector ahead of this warm front. This is the upper level flow. There's a ridge at 750 millibars. You can see basically westerly flow. And this is a vertical cross-section along this line from the coast to, I guess, northwest Wyoming. And you can see the sloping terrain there. Color field is the relative humidity. It also shows the theta E contours in black, and then the meridional wind in the purple contours. The area of interest is a small area with the terrain right here. So deep moist flow, essentially. In terms of vapor transport, actually qualifying as an atmospheric river. These are soundings from the site in the area of interest, Crouch it's called. showing basically that, let's look at the maybe the temperature profile shows a little inversion here. You can see theta E increasing with height. The red is the model. Black is observations, radio sonde observations, and you can see they match reasonably well. Scorer parameter is important. If it goes negative at some level, that would imply a trapping mechanism for gravity waves, and we don't really see that going negative. So it's close to moist neutral, but it's stratified, more stratified at low levels at the Brunt-Väisälä frequency. Fairly strong winds aloft up to 40 meters per second. All right, so now clouds and precipitation. Reflectivity on the right side. Remember, all these waves up and down in vertical velocity, we don't really see a similar wave pattern in reflectivity. So to a first order, the microphysics don't respond to these waves in an apparent manner in terms of reflectivity. And the reason for that, I think, is that the time scale of advection through these waves is relatively short. It's on the order of 5 minutes compared to the time scale of microphysical growth. So these snow particles don't really have the time to evaporate on the downwind side in these waves that you saw earlier and grow much on the upwind side. The liquid water, supersaturation, certainly responds very quickly to these vertical motions, but the reflectivity, which is really the result of snow, is due to the scattering particles that produce reflectivity. They don't respond all that much. You don't see a maximum in these waves. It's more like a continuous stratiform precipitation system. Model 2 looks very similar. There's a slight maximum here associated with that resonant wave that we see in that valley and associated with peaks 5 and 6 maybe. And the observations have that too. You can see the sloping freezing level, and that also explains why, I didn't mention this, I can go back to it real quick. I think you may have asked about this. This is contamination here due to the sloping freezing or melting level. Remember, do we subtract a height-dependent uniform fall speed? At this level, we assume a fall speed that is a mixture of rain and snow falling. And so where snow is falling out here, it's basically subtract too much of a fall speed and then it produces an artificial updraft. Whereas here where rain is falling at that level, it produces a downdraft. So that's a contamination or an artifact of our simplified approach in estimating the vertical air velocity. Anyway, moving back to where I left off. So there's no clear relationship. Well, maybe some enhancement there in reflectivity, but otherwise you don't see that wave pattern. Unlike, for instance, lenticular waves, Lee wave clouds, where you see a clear.
Those scales, they're so different.
The scales in the horizontal and the vertical, they should be the same.
Look like a 20 DVZ.
Oh, okay. Yeah,
20 and
that
20,
one, yes.
not even close.
That's right. That's a good point. So the reflectivity is from the model. It's essentially assuming well, it assumes a longer wavelength. It assumes Rayleigh scattering, no Mie scattering. Basically, weather radar. It's the product called reflectivity in the model output that's based on the size distribution of the hydrometeors. And it's basically for S-band or C-band, but not for W-band. W-band reflectivity is much lower, so only look at the patterns, but not the magnitude. Thanks for pointing that out. Yeah. It's just Rayleigh scattering, whereas Mie scattering is really important for these larger snowflakes at W-band. So let's just look at the pattern. Okay, so where did I leave off? Oh yeah, when you look at lenticular waves, and granted the vertical velocity variations are large here, you can really see a modulation of the reflectivity by the waves. Here we don't see that. Basically there's snow all across the area at a given level, and the snow doesn't really grow or shrink all that much. in the waves that we observe. But nevertheless, we know that we think that at the surface, there's significant modulation of the precipitation by the terrain. The ridges have, maybe a factor of 2 more precipitation than at the surface, according to PRISM at least. That's what they suggest. So the reflectivity doesn't suggest that. If you retrieve reflectivity based on this, basically it's fairly uniform, more on the right over the mountains than on the left. But otherwise, it doesn't seem to capture these finer scale ridges. Now, when you look at liquid water content in the model, you do see maxima with every ridge and this resonant wave. Here's the resonant wave. So the liquid water responds in the model to these small scale vertical velocities. And liquid disappears in the downdrafts. Liquid is confined to lower levels primarily. And I guess one main takeaway from this work is that according to the model, and I guess observations suggest that we really don't know much about precipitation growth in that lowest level where we cannot fly. Minimum flight level is something like 2,000 feet above the highest terrain in IFR conditions, and that puts you above much of the liquid. So in terms of that orographic enhancement, you cannot really measure that, in situ at least. But even with the radar, we're challenged to find any signal. And with the WCR, we can actually look very far down into the valleys. But we don't see much of a signal. So it's a bit of a mystery what, if any enhancement exists over those ridges. Looking at flight level observations. Now, when flight levels varied, we flew back and forth on the same track, but not at the same level. These black marks here indicate the various flight levels where we flew along that fixed track. So the in situ measurements of ice and liquid water content, they are from a mixture of levels. And on this flight, there really wasn't much liquid, less than 0.05. These are observations. Ice comes from the Nesterov, liquid comes from the CDP. And then the vertical velocity at flight level from the GUSS probe. We removed the mean. And, does it correspond with, for instance, this updraft seems to correspond with that maximum in liquid. Maybe this one as well. You expect a maximum in liquid to occur maybe towards the end of the updraft. And that seems to occur. Model, liquid water for the Thomson scheme is much higher. That's a dashed line. Ice corresponds fairly well, mixing ratios. But then the model also had a higher amplitude vertical velocity, as I told you earlier. So it may be that the model was too aggressive in terms of vertical motions, and that might explain why it has too much liquid. But that's pretty subtle because, there's other factors that may come into play. How good is the microphysics scheme? In terms of surface precipitation, then, we don't really measure that with the radar. We have a ZS relationship we can use, and this is one that was developed for the W-band radar. The model does produce well-defined maxima at or just downwind of the peaks. And this corresponds with that resonant wave. This maximum corresponds with that ridge, and that corresponds with that ridge. So the ridges do seem to have more snowfall or precipitation in a model. We don't see that in the radar signal, so which one is correct here? And I would argue that the model in this case might actually be more correct or more reliable than the observations, even though, we look far down into the valley. For one, this ZS relationship is applied just above the melting level. We cannot really do this reliably below the melting level. So a better case would have been where snow occurs. A second one, first one here, is hydrometeor sorting. The idea that we use a single ZS relationship or ZR relationship, but in fact these constants may differ depending on your hydrometeor mix. And if there is supercooled liquid present, then you may have more graupel here. And the model actually shows graupel being present in these ridges. I forgot to mention that. And so graupel falls out faster than snow, and so you have a different type of hydrometeor mix down there. So the model, the ZR relationship may not be representative. And another factor might be the fact that WCR, W-band reflectivity, is actually attenuated by liquid, and we know there's liquid at low levels, so looking down, in some places, the reflectivity is underestimated because of that liquid water attenuation. And from the black towards the red, that's a correction for that liquid water content attenuation. It's 10 dBz per gram per kilogram of liquid water per kilometer. And in places where there's a fair bit of liquid, it jumps up. And so you see some modulation now that corresponds with the observed surface precipitation variation. But I think the main reason is that we estimate the Z-S relationship a little bit too high at 2.5 kilometers just above the melting zone, whereas the maxima in liquid are really mostly at lower levels. So notwithstanding these really high quality observations, there's still uncertainty as to whether this orographic precipitation enhancement that the model demonstrates there is real. So, yeah.
CS relationship could be changing a lot.
Yeah. Depending on your hydrometeor mix. Yeah. So, yeah, but we don't have in situ measurements down there. The model suggests there is some graupel in these patches. Yeah. We did this for one flight and then for 3 other flights. Here is a second flight, and I'm not going to go through the details because don't have much time left here. But these 2 flights look very similar. If you look at just vertical velocity patterns, first of all, it's similar to the flight RF-23. RF-11 was the 4th of February, I think. And there's some predictability to this. Under similar flow patterns, similar stratification patterns, you have similar vertical velocity patterns. This was actually a colder case. The freezing level was lower, as you can see. And we can estimate precipitation at the surface a little better. The amplitude of the vertical velocities in the models was again a little bit too high, but otherwise the pattern looks very similar in the model compared to observations. In terms of surface, flight level observations of liquid, the model again overpredicts the amount of liquid in these spikes, in these updrafts, that maybe because the updrafts are too strong, as I mentioned before. Otherwise, the correspondence is really quite good for the cloud microphysics. And in terms of the surface precipitation correspondence, again, the model produces more of a modulation by the terrain. That's a black line compared to the observations in blue. Then we looked at 2 patterns in the southwest to northeast direction, track B. I don't think I'll go into detail. This was the warmest case we had. But in all these cases, we have this low-level convergence. So there's some mesoscale updraft. And we have a similar wave pattern, vertically propagating waves. Downwind of ridges. In this case, more of the precipitation occurred on the eastern side, the lower slopes rather than the high slopes, because there was a lot of liquid and graupel in the model. This was a case with lots of liquid at flight level, and especially in the model there was a lot of liquid here. And then fairly heavy precipitation at the surface. In the interest of time, I'd like to have the floor open to questions soon. I'm just going to go to a summary here. Basically, what I've demonstrated is a novel way of estimating vertical air motion from a profiling airborne radar with an assumption, well, 2 assumptions really. One is that you ignore this mesoscale vertical motion over the distance of, say, 100 kilometers. That's the length of the legs. But you cannot measure that accurately anyway, so although an independent estimate of W bar could be added, like from a model. So we have a fairly good understanding of vertical motion. And the reason why I emphasize vertical motion is because it drives the microphysics. If you want to validate microphysics in a model against observations, you really want to make sure that the vertical velocities are captured well, first and foremost in the model before you go through the various microphysical parameterizations. And WCR vertical transects actually look very much like the model, but not so much instantaneous ones, but rather the compositing one. So one thing I've learned from this field campaign, that if you want to validate microphysics and vertical motion in systems where there's a lot of transient signals, such as, well, frontal disturbance, stratiform systems, and a fortiori maybe convective systems, you really want to composite as much as you can. You fly the same tracks back and forth to build up a data set that allows you to make the comparisons against the model output. So your signal is not dominated by the transient noise. It's not really noise. These are real features such as the Kelvin-Helmholtz waves and the turbulence and these cloud top generating cells. They're real, and they may well be important in microphysics, but in order to compare against model output that does not have these fine scale features, you really want to composite. And there is precipitation enhancement according to the model, and that is consistent also in general with the prism climatology, peaking at or just downwind of the individual ridges. And that seems to be the result of very shallow precipitation growth mechanisms at the level that is too low for aircraft to measure. And finally, reflectivity, sampled at the lowest meaningful level, that's above the melting level, shows some modulation by the terrain, but weaker. So it may not be a good proxy for precipitation distribution because of attenuation by liquid, hydrometeor sorting, and then also the fact that we don't quite measure it low enough. That's all I have. Oh, do you want to use the...
No, you're fine. Thank you very much, Bart, for your excellent presentation on vertical velocity motions using aircraft observations as well as the models. If anybody has any questions, please raise your hand in the audience, and I have a microphone because this is being recorded. And for those watching virtually, you're using the Slido window below your presentation screen, and I can read it from my laptop. Does anybody have any questions for Bart? Vivek.
Yeah, Bart, could you comment on the temporal and spatial scales of vertical air motion estimate, what you can do in stratiform or convective precipitation events? What kind of temporal solution you can get this one out of it?
What?
The vertical air motion.
Yeah, well, we have tremendous time and space resolution with our aircraft observations. And, spatially, it's in vertical transect. So these are snapshots, essentially, almost synchronous measurements, even though the flight track to complete takes on the order of 15 minutes. Back and forth, that time resolution from one to the next is on the order of 15 to 20 minutes. That's the time it takes for us to repeat the flight leg. Is that what you're asking?
Yeah, if you want to represent in terms of, for a precipitation event.
Yeah. Yeah.
What is the resolution you can come up with? Because you got averaging quite a bit in temporal and spatial scales. And
so at that time scale, if you average over the duration of the flight, 3.5 hours, then over that time there may be some synoptic changes. Certainly, if it's convection, that convection evolves. But if it's small scale convection, like in cold air outbreaks, one cumulus after the other, then averaging over that time scale, I think is sufficient. In some cases, we saw that our averaging over, say, 10 transects is not quite enough to totally suppress the transient signal. Sometimes you could see some streaks of enhanced reflectivity that come from one or two of these transects contributing to the cluster of 10. So, but that's all we could afford. In general, the target weather systems was such that there was very little variation. We wanted to look at relatively persistent rainy periods like in the warm sector orographic precipitation environments, not sudden frontal boundaries.
Thanks, Bart.
I think we have a question in the audience from Lou, and then we have Tammy online. I think Lou was just yawning, was just stretching. John was just stretching. We have a question online. I'll first ask from Tammy. Okay. So we have a question from Tammy Weckworth, and she says, "Thanks, Bart. That was great. What is your plan for next steps to reconcile observations and model precipitation?"
Oh, that's a good question. In general, I think the way forward here is to go to eddy resolving numerical simulations, large eddy simulations that can capture these transient features that we see in the WCR transects and flight level. There's a lot of transient signal there in the vertical motion and also in the cloud and precipitation field. And so LES should be able to capture that. But then comparing to LES, you really need to have a sufficient sample size again to capture the full distributions and the response of the mesoscale terrain. So with the LES model output, you'd have to do the same as what we do with the cloud radar data that is average over time, such that the transients are suppressed and the stationary terrain-driven features come to stand out. But that would be the next step, to use the much higher resolution eddy resolving simulations, and you don't depend on the boundary layer parameterizations. Because much of the growth apparently happens at low levels. Even though you have vertically propagating waves going up to the upper troposphere, much of the growth appears to occur very close to the terrain, and the transient features there, they may well be important in the microphysics. So ultimately, I think the way forward is that LES be validated against radar transects, such as from WCR, but then averaged over time such that you have a sufficient sample size, you have the distributions, and then use the LES as a dynamically consistent model output to evaluate model parameterizations. So LES would be sort of the middle building block, if you like, of evaluating these many different microphysics parameterizations that exist out there.
So as a non-meteorologist, I'm here trying to understand the work's implication, right? So I think it's Tammy, right? Just asked the question.
That was Tammy, yeah.
Yeah. So in part, probably it's very similar. So you're maybe already answering that. So because from the final few slides, it looks like the vertical winds in the model is doing pretty well, if I hear what you said. So since the vertical winds are doing pretty well, so have you zoomed into what happened in the models that misses the actual precipitation? So is that related to the question you just answered? So, what after this experiment have you learned in terms of models deficiency or the issues of not forecasting or modeling the rainfall precipitations?
Yeah. Well, my main message is that the first step you want to do is validate your vertical velocity pattern well before you look at different microphysics schemes, because you may be finding a microphysics scheme that matches the observed radar reflectivity very well, but it may be for the wrong reasons. The model may have the wrong vertical velocity pattern, so you want to have that right first. Although I must say that vertical velocity is tightly coupled with the microphysics. In a dry atmosphere, you would still get gravity waves, but probably not the same amplitude, right? Because the moisture changes the stratification. You have a moist adiabatic neutral lapse rate as opposed to a dry adiabatic one. to compare against. So the Brunt-Weisselab frequency would be different, so the wave amplitude would probably be different. So it's not a simple answer. But still, I would first try to validate the vertical velocity patterns.
So this, you're still on your way to address that question you open up of,
Yeah.
complex terrain
Yeah.
precipitation pattern.
Yeah.
But now you rule out the vertical velocity, you have to go next step to other things, right? Is that
Yeah.
what the message is? And
Yeah, these measurements are, by nature, they're from aircraft especially, they're so short term. You really have to compare to the highest resolution possible in terms of model simulations, the LES simulations, and use them as building blocks to evaluate the coarser models. That applies for cloud and precipitation processes, but it might apply to atmospheric chemistry as well. And once you have the model right, then you can go towards that question of how well does the seasonal precipitation compare to, for instance, PRISM gauge network for the entire season. But you start off with these very small time-scale observations that are really focused on the validation of processes. And in this case, emphasis is on vertical motions as prerequisite to validate the cloud and precipitation.
thank you.
Are there additional measurements that you would like to have to better characterize your vertical motions and microphysical processes?
Yeah. Ultimately, combination of surface networks with airborne measurements would be great. We hardly had any measurements over the terrain here in Snowy. It would be good to measure size distributions of precipitation over the terrain at multiple places. And as far as measurements in that terra incognita, if you like, between the lowest flight level in cloud and the terrain is concerned, that's a very difficult one. I think remote sensing is the best way to go. You could go drones, I suppose, or even tethered balloons, although that would be difficult in clouds and precipitation.
Hey, Matt.
You've mentioned validating the model with observations a few times, but methodologically, what are you doing to perform an analytical validation? Or are you just looking at the image and saying, yeah, that looks about the same?
Yeah, these differences, especially in cloud, liquid water content, ice water content, they're so large. I showed a few examples, right, at flight level. That's the only place where we can validate because we have flight level measurements of those quantities. The differences are really so large, even though the vertical velocities correspond fairly well.
But even the vertical velocities, like, how are you evaluating that?
Yeah, it's not a quantitative comparison. I can give percentages of difference in magnitude, but you're thinking of a more quantitative comparison, right?
Right.
Yeah, microphysical schemes are really first-order comparisons. If I were to use, and in fact, Lulin has done that, tried a different microphysics scheme, like the Morrison scheme. You'd get quite different answers in liquid water, ice water content. So I think a more quantitative comparison is, we're not at that stage yet. Yeah, uncertainties in these quantitative water properties in clouds, precipitation and cloud size distributions, just mass concentrations, they just differ a lot between the various parameterizations for a given flow field.
Anybody have any further questions from the audience? Not.
I just have a comment. This precipitation was the snow and our supercool liquid, small drops. And what you see is mainly the snow in this case. You don't see much of the small particles, which are, again, more important for the growth and rhyming, other things. And so you are kind of limited with your measurements. Did you look into I thought you had radiometers, is that right, for these measurements and ground-based radiometers?
Yeah, we
for
did
liquid-
have radiometers, multiple
maybe that
radiometers,
could
yes.
give you
that gives you
additional-
some indication of liquid water path.
Okay.
Yeah, and that we validated that against the model.
Okay. Okay.
But remember, liquid water is very local. Radiometer was, in fact, upstream of this area, towards the western end of the transects. And there's been some validation there.
Okay.
But then,
Yeah.
unlike snow, a liquid tends to be far more concentrated in small areas because it's more responsive to the vertical motions, the changes in
That's right.
humidity, supersaturation, right? Yeah.
Thanks.
Anybody have any further questions from the audience? There's none from Slido. Great. While we're at the seminar hour, I'd like to thank Dr. Geerts for his excellent presentation on vertical motions. It was very comprehensive. On behalf of EOL, I'd like to thank you. So let's give our speaker a final applause.